Here looking at a problem from the 1998 AP exam, this from the multiple choice. I chose this problem because it can be solved multiple ways, and I want to show you those. It'll serve as a good review of some of the concepts discussed so far in your physics class. First route we'll take is through kinematics and dynamics, or forces, and the second route we'll take is through energy and work. The problem itself deals with an elevator. We are given the mass of the elevator. We are given that it is initially moving downward with speed vi, and as this cable pulls upward with a tension of 11,000 newtons, that'll make the elevator slow down, and after 8 meters, it's going to come to rest. So our goal is to find that initial speed value, vi. We have 5 potential answer choices, and we'll take route number 1 through kinematics and dynamics. I can see why a lot of students might use kinematics here. We're solving for a velocity, we're given this height. Those are both kinematic variables. So when we go that route, we should start with a list. These are the 6 kinematic variables. Let's plug in what we know so far. We begin with an initial vertical position of 8 meters, and we end with a vertical position of 0 meters. Our final velocity is 0, and our initial velocity is what we're looking for. So we know some things, but we don't know enough to use our kinematic equations yet. We're going to need to solve for one of these 2 blanks to have a chance to use our kinematic equations. And I think acceleration is a good one to go after because we can find acceleration through an analysis of forces. So starting with forces, our focus is on the elevator as our object. I can think of 2 forces that act on the elevator, a downward force of gravity from Earth and an upward tension force from the cable. Well, again, this elevator is slowing to a stop. So what would make it slow to a stop? We would need more upward force than downward force. So I know that the tension is greater in magnitude than the gravitational force. I'm drawing my vectors with those appropriate lengths. I'm stating as much here. So I'll need a net force equation, which is large minus small. Here, Ft minus Fg. Here I'm just copying the equation to make it easier to sub into. I see the variables net force and gravitational force. So I'll need to go to my formula sheet and select the weight equation and Newton's second law. Here I'm making those substitutions. Now I'm analyzing the given information, which is mass, tension force, and Earth's gravitational constant. Now in a lot of questions, you'll use 9.8 for this value. In multiple choice, a lot of times you'll see them round this number up to 10 just because it makes the answers look nicer. Look at these 5 choices. There's no decimals in them, so consider using 10 for multiple choice questions. From there, I have everything I need other than this acceleration value. Punching in what I know, doing the algebra, gets me a value of 1 meter per second squared. Now that I have found my acceleration value, I can plug it back into my kinematic list. The best kinematic equation to choose with this particular list would be this one here. I like it because it relates the variables I know or am looking for, and it leaves out the only variable that I don't really care about here, which is time. I don't know a value for it. I'm not looking for it, so let's avoid the t variable. Here I'm just making the equation stand out so I can plug into it. Here are the numbers from the list put into the correct locations, and now we just need to do the algebra, solve for variable VO, and doing so you'll get an answer of 4 meters per second for choice A. As mentioned, there is a second route that we can take to prove this answer of 4 meters per second. So I will show you a second way to go from the energy and work unit. To begin, we need to establish our energy system. I will choose the elevator, which is our object, and Earth. We also need to define our moments. Moment A will be the 8-meter height point, and moment B will be the 0-meter height point, or what is our reference point. From there, let's track which energy forms are present at each moment. Starting with moment A, we have a height above our reference point, so we have a gravitational potential energy in our system. We also have a moving object, so we have a kinetic energy in our system. Now looking at moment B, we have lost the gravitational energy because we are at the reference point, or the height of 0, and we have lost our kinetic energy because we now have a velocity of 0. So here we have a clear change of energy. We had some energy in moment A, and we have no energy in moment B. So something external to our system is doing work and is changing the energy. So we'll need this equation from our formula sheet, just establishing that below. And now we can focus on the energy change as final minus initial. Our final energy is 0. Our initial energy is the addition of gravitational and kinetic. Okay, something did work, but what did the work? What is external to our system that is the reason that this elevator slowed down? Well, we focus on our work equation. We need to find the force that did it. I would think it's the cable that is external to our system and doing the work that provides this upward tension force. This is the reason the system slowed down. So as we plug into our work formula, notice I'm using the tension force specifically, the displacement over which it acted, and now the cosine of theta. Looking at what we have so far, I see the variables for gravitational potential energy and kinetic energy. Going to the formula sheet, we will need these two equations as substitutions. So here I'm making those. On the left side of my equation, I have negative what will be mgh. This negative also factors in here, gets me minus 1/2 mv squared. And I'm just keeping what I had here on the right side. Let's look at the given information to plug in. First is the tension force value. We know it points upward, and we were given a value of 11,000 newtons. Secondly would be the displacement. This elevator has moved downward 8 meters. That would also represent the height variable h, so both h and delta x, I will use a magnitude of 8. Directionally, we've got to focus on theta, which is the angle difference between the tension force direction and the displacement direction. Well, tension force acts upward, the displacement is downward. That is an angular difference of 180 degrees, so I will plug that in for theta. We were given the mass and the gravitational constant, we always know. Again, we'll use 10 for multiple choice. I'm just plugging these things in, solving for velocity v, and I wind up with the same answer, 4 meters per second. To summarize, as we get deeper into the physics year and we learn more and more concepts, we will often run into questions that can be solved multiple ways. This is an example of that. So it is up to you as the question solver to choose the route that you are more comfortable with, whether that be kinematics and forces on the left or energy and work on the right. You're thinking about which you can do more accurately, of course, but also which you can do in a quicker amount of time because there is a time limit for the multiple choice section. If you found this video helpful, then I have other resources that you may be interested in as well. For more information, check out my website, shoot me an email, or follow me on X and Facebook. All of the links can be found in the video description.